I want to thank everyone for joining us today for our webinar and trivia, Keep It Cool, Thermal Management for Power Supplies. This is a special session because we obviously have here Bob White from Embedded Power Labs. We're also going to be hosting a trivia session at the end of the training for all of you who want to participate in the trivia. There will be a prize, and the prize is a Yeti cooler. So we're very excited that we were able to make the connection between thermal management and giving out a nice cooler. So if you want to participate, please stay until the end. And now I just want to quickly introduce our speakers today. So Bob White has more than 40 years of experience in designing power supplies, DC converters, and power systems for electronic equipment. Currently, Bob is the president and chief of Embedded Power Labs, a consulting and design service company. He also teaches power electronics for master's degree students at the University of Colorado. So shout out for everyone joining us from Colorado. We're excited to have you. And we also have on the call Matt Furman. He's our mechanical engineering manager here at Astrodyne TDI. He completed his bachelor's and master's degree in engineering from Binghamton University and has been working with us in making electronic packaging for over 10 years. And without further ado, I'll pass it over to Bob, who will be starting the session to teach you guys a little bit of his experience with thermal management and give you more information about what we have to offer.
Thank you, Monica, for the kind introduction. So yeah, today we're going to be talking about thermal management, and just to kind of summary, give you a little preview. First, the theme here is heat is not your friend, and we're going to talk quite a bit about the effects of heat on power supplies and electronics in general. We're going to talk about the ways of moving heat and some of the modeling, some of the simple modeling, so that we can make these predictions. The various ways that we can move heat, and then do a little deeper dive on convection and conduction cooling in particular, because these are the most commonly used. And we'll close out with just a few brief comments on how to actually measure temperature and airflow, because you can't manage it if you can't measure it, right? So why is thermal management so important? Well, I mean, as I said, heat is not your friend, okay? It increases the failure rate, and it causes a shorter service life. And all of this translates into a higher cost. And it's not, and that cost is for your customer. I mean, if you're buying one of these power supplies, you're putting it into your equipment. When that power supply fails, it's not just a power supply failure to your customer, it's an equipment failure. So it's a cost to the customer, and it's also a cost to you, because now you've got to replace that equipment for your customer. So managing heat is really important. So let's talk about heat and reliability. And the way we typically model reliability is something called the bathtub curve. And it has three basic segments. So the first is what's called the early life failures. And that is right at the first time it's manufactured, the failure rate tends to be a little bit high. So and those need to be weeded out quickly. And this really is the manufacturer's responsibility to get these failures out before they get into you, the customer, okay? And they got to do that by using quality components and materials, controlling your manufacturing processes, and when necessary, burn-in testing. Say, Matt, so I know Astrodyne is really concerned about reliability and quality. What does Astrodyne do to make sure these early life failures don't get out to the customer?
Absolutely, Bob. So here at Astrodyne TDI, we employ what we call HASS testing, which stands for Highly Accelerated Stress Screening. And really what that is we take our power supplies after they're completed, we put them in an environmental chamber where they're subjected to temperature cycling, load cycling, so powering the unit on and off, as well as some high frequency vibration. And what that does is it simulates the first portion of the power supply's life cycle. And the end goal is to weed out any manufacturing defects that may have taken place somewhere along the process. And one of those defects, they could be cold solder joints, bad solder joints, miswires, loose wires, anything that may, the power supply may see early in its life.
Okay. Sounds like a pretty extensive process, but it's quite effective, right?
Correct. Yes.
Yeah. Okay. So after that, after the product is now out in your hands, customer, what happens then? Well, we have a period in which the failure rate is essentially constant, and we call this the normal service life. Okay. So during this time, it's defined by this constant failure rate. So we might talk about that in terms of mean time between failure. That's the most common metric. This is strictly for replaceable equipment, but we also talk about mean time to failure, or you might even hear the term FITS, failures in time. They're all talking about the rate at which we have failures. And it's important to really understand what MTBF is. So let's say the MTBF is specified as 250,000 hours. I mean, that's almost 30 years. And that's a long time. You might say, wow, I'm buying this power supply. It's got 250,000 hour MTBF. It's going to last 30 years. Not exactly, right? This is not 28.5 years. That's not what MTBF means. It's a rate. So if we have, like, say, 1,000 units out in the field operating around the clock for a year, that's almost 9 million unit operating hours. And so during that time, we would expect to have about 35 failures. And so this is the importance of understanding MTBF and rate. So that's 35 failures that, even with an MTBF of 250,000 hours, if you have these units, you're going to have these failures.
So Bob, that's a standard MTBF. Can you explain how temperature would have an effect on the MTBF?
Exactly. I opened by saying heat is our enemy, right? So how bad is it? I mean, if we increase the operating temperature, say by 10 degrees C, just 10 degrees C, the failure rate approximately doubles. Okay. Now there's a lot of details in that, but that's a pretty good rule of thumb. And so that means the MTBF is decreased now to 125,000 hours. And those 1,000 units we had operating in the field for a year, now there's 70 failures we can expect. So that's pretty severe just for 10 degrees C. And this highlights the key importance of managing the temperature, of the thermal management. This right here tells the story. Okay. Now, after the normal service life, equipment enters this end of life and things start wearing out. And this is beyond the normal life. The failure rate now starts increasing rapidly. For power supplies, there are two common things that wear out. First of all, aluminum electrolyte capacitors are very reliable during their service life, but eventually the liquid electrolyte dries out and they start becoming less of a capacitor. They start failing. The other is fans. Fans are mechanical machines. They are rotating machines. They've got some sort of bearing. It can be a high quality ball bearing, it can be an expensive sleeve bearing, but eventually that bearing is going to wear out. So eventually we do come to an end of life wear out.
Okay. Is it fairly safe to assume that the temperature would have a similar effect on the service life or the end of life as it did on the MTBF?
Matt, exactly true. I mean, if we increase the temperature by 10 degrees C, what we see is the service life is about halved. Okay? So that's pretty radical. And so just 10 degrees C has this very large impact on reliability in life. And so this theme of heat is your enemy and the need to manage the temperature is just is so important. 10 degrees makes a huge difference. So if we're going to manage it, we got to be able to kind of make predictions, model it, and measure it. And it turns out, it's actually not all that complicated. We can do some really good modeling and approximations without getting deep into the physics of the thermodynamics. Now, as I'm an electrical engineer, and so, I can look at this circuit and I can understand what's going on here pretty quickly. I've got two voltage sources connected by a resistor, and so there's some current flowing. That current's proportional to the difference in voltage divided by the resistance. Well, you know what? We can model thermal systems in the same way. If we have like two different temperatures and they're connected by some heat conducting path, maybe some sort of thermal pad, or it could be even more of an insulator. There's going to be some power flow. There's going to be a heat flow from one of the temperature sources to the other, and it flows through this thermal path we can characterize by a thermal impedance or a thermal resistance measured in degrees C per watt. And we can write exactly the same equation. The heat flow is proportional to the difference in temperature divided by the thermal resistance. So the heat is going to flow from the hotter to the cooler, and how much heat flows is proportional to the difference and that thermal resistance. And so we need to manage that thermal resistance. And so if we look at now a case of where we have like a power dissipation, that might be like a power supply. And the heat is flowing out of that power supply. It's dissipating heat internally. It's flowing out through some thermal resistance to some fixed temperature. Okay? And we can write now the temperature of the power supply. This is just like writing the Ohm's law's equations. I mean, this is so for as electrical, we can just look at this and do this modeling. And you know what? As simplistic as this is, it actually works really well. I mean, we can get very good results with these simple models. And this is just like modeling a current source flowing through a resistance into a voltage. So we can predict temperature if we know the thermal impedance, we know the power dissipation, we know the heat, where the heat's flowing into. So what is the heat flowing into? Well, from that heat source, like a power supply that's operating and dissipating power internally, most often that T0, that we're pouring the heat into the surrounding air, into the ambient air. And so T0 would be the ambient temperature. Now, it's important that that ambient temperature be recognized as the temperature right at the power supply. So if the power supply is in a box, it's the temperature in the box, not the temperature in the room. We'll talk more about that in a little bit. Okay. So when we do this, when we transfer heat out into the surrounding air, this is called convection cooling. Now, sometimes that doesn't work good enough for us. We'll talk about that in a moment. So for higher power, if we need to be able to remove more heat than we can just put into the air, we use a cold plate, or sometimes called a base plate. And we move that heat into that cold or base plate where that can be removed more efficiently. And we call this conduction cooling. So the other way that we can get heat out of something is called radiation cooling. Anything that's above absolute zero is radiating heat to some degree. And in fact, that's what we use when we use thermal cameras to take a picture of equipment. We're actually measuring the infrared radiation. We're measuring that heat being emitted. And so we get a little bit of cooling. We can get a little bit of cooling by what's called radiation. And if we want to improve it, then we can, if we black anodize, say, an aluminum heat sink, we will improve that amount of heat being dissipated. But compared to convection and conduction, this is marginal. We can get a little bit of benefit from this, but for most applications, this is not how we're going to get most of our heat out of it. But if you need a little extra margin, and we'll see an example later, it helps. Okay. So natural convection cooling, we have a power supply, and we just have air kind of dissipating and flowing by it. So the air is surrounding the power supply is dissipating heat. It heats up the air, hot air rises, so it kind of moves away from the power supply and cooler air moves in. So when we just kind of let this happen naturally, we call it natural convection. And there's a lot of advantages here. I mean, there's no extra cost, right? This basically comes for free. And there's no fan noise, right? There's no fan blowing air around. But the limitation is we can't get a lot of heat out this way. I mean, we are limited in the amount of heat removal capability. So how can we do better? Well, we can add that fan, and now we can force air to flow. We can blow air across the power supply. And so instead of just relying on the action of heating up the air and letting it move away, now we're forcibly moving the air away and constantly bringing in cooler air. And this forced convection actually gives us a much higher heat removal capability. So this is the next step up from natural convection is forced convection. Now the disadvantage is that we have the extra cost of the fan, and fans make noise. So that has to be managed. Okay? And if we want to go even, so how much better is forced convection versus natural convection? So I have here a couple of curves that you might see for like a heat sink. And this is a hypothetical heat sink. And there's a curve for natural convection, and there's a curve for forced convection. So under natural convection, if we were dissipating 5 watts, this curve tells us that the temperature rise would be about 28 degrees, or a thermal impedance of 5.6 degrees C per watt. But if we had the same heat sink, and now we add a fan, and we start moving air at, say, 200 linear feet per minute, about a meter per second, and this is not a lot of air. This is a kind of a pretty standard kind of airflow. We see that the heat sink's curve says the thermal impedance is now 3.25 degrees C per watt. That's a pretty significant improvement. And the temperature rise for that same 5 watts of dissipation would now be about 16 degrees C. That's 12 degrees C cooler. Well, that's a lot, because we said 10 degrees C makes a big difference. I mean, if you're 10 degrees C cooler, then you've greatly improved your failure rate and greatly improved your service life. But it did come at the cost of a fan. So fans tend to be a little bit misunderstood. They all come with a fan performance curve, because a fan pulls in air. It's like a pump. It's pumping air from one side to the other, and we end up with a pressure drop from the outlet to the inlet side. And so when you buy a fan and you say like, well, it's a 30 CFM fan, that's what the data sheet says, that's measured with absolutely no pressure drop. That's just totally free flow. The fan is sitting on an open table or open bench, and it's just moving air with no obstruction whatsoever. But let's take an extreme case. I'm going to put that fan and I'm going to hook it up to like a completely sealed enclosure, and I'm going to have the fan blowing air into the enclosure. What happens? Well, eventually the air pressure inside, we're pumping air in, the air pressure increases, and eventually there's actually no airflow. So now we're at the other end of that curve. Okay? So there's no airflow at all. You said, I bought a 30 CFM fan. Well, of course, this is an extreme case. Now, nobody's going to do this really. So let's go back and let's consider a more open enclosure. Again, the airflow is pretty freely, but it's not perfectly free. There's some enclosure. We get a little bit of back pressure. Okay, and now maybe we're at 26 or 27 CFM. We're still not getting the 30 CFM the fan was rated for. But again, this isn't very realistic either. I mean, most enclosures, we're going to have vents on the side is going to be closed up, so you can't like stick your fingers in. We're going to have vents to get the air out. So the fan's going to pump air in. Now the airflow is even more restricted. The air pressure is going to build up because it takes pressure to move air through these vents. Now we might be down here. So you bought a 30 CFM fan. If you're not careful, even in a pretty good enclosure, you might only get half that airflow. Now, and even more typically, when we have a circuit board in there, power supply, we've got components, there's even more restrictions and even more back pressure. And you could end up at a fraction of the airflow. And why is this important? Well, because there's an inlet temperature. Your equipment's operating in an office or a data center or in some industrial facility. It's taking in air from the room at some temperature. It's moving that air through the enclosure, over the electronics, past the power supply, and it's picking up heat, and it's being exhausted at a higher temperature. A lot of times we have a specification on the maximum outlet temperature. For example, in my experience, 10 degrees C, that the temperature rise across the box can be no more than 10 degrees C. And that temperature rise is proportional to the amount of power and inversely proportional to the CFM. So if we have more CFM, we get less temperature rise. So if you design, like basically saying, well, I got so many watts and I got this temperature rise, I need this CFM, and you go buy a 30 CFM fan, but you put it in this enclosure and you're only getting 5 CFM, now you got a surprise, and now you're much hotter. And so, Matt, I understand this has kind of been, you've seen this kind of issue in applications in the past, right?
That's correct. Yep.
Yeah.
PC boards that, your the area that you're blowing the fan over acts as your duct, and the more you restrict your duct, the more back pressure you're going to get. So yeah.
And the more pressure you have, the higher the pressure, the less the air. Mm-hmm. So yeah, so this is actually a very key and important. I think this is one of the key things we want you to take away from this seminar today is managing the airflow and understanding that just because you bought a 30 CFM fan, you're not going to get 30 CFM. Managing the air pressure drop. Now, the other thing that we need to understand is power supply derating curves. And you'll see these are pretty typical. So in this region of the curve, you can get full power, up to some ambient temperature. And again, the ambient is the temperature around the power supply. It's not the temperature in the room. Power supply is inside in the enclosure. It's the local temperature to the power supply. And what the manufacturer is telling you here is they're saying, hey, for up to 45 degrees C, the internal temperature of the power supply is in that range that we can guarantee the reliability in the service life. So full power all the way up to 45 degrees C. But that internal temperature here, at this point, you go beyond 45, and now that internal temperature is going to become higher. And just going back to that very simple thermal modeling we had before, if we need a higher ambient, you've got to reduce the internal temperature to keep that internal temperature within the range where you'll get the desired reliability and service life. And so with this hypothetical kind of derating curve, if we needed to operate this power supply in a 50 degrees C environment, then you could only get about 62% of its rated output power. So it's important then to understand this and make sure that you operate your power supplies within their derating to get the desired reliability and service life. And there's similar curves with forced convection. Again, here's proportional to the airflow. The more air you can move, the more heat you can take out, you can operate at a higher power, but eventually you'll have this same sort of break point where you'll have to start reducing the output power to keep the internal temperature at the temperature that will keep the reliability and service life. Now, if we go beyond the limits, if we've got really, some special cases, like we've got very high power dissipation. Or there's a lot of applications where we need a totally sealed enclosure, like might be a corrosive atmosphere in an industrial environment, might be a wet environment in some sort of manufacturing plant, might even have to be totally submerged. So in this case, we're not going to be able to blow air through here. No amount of forced or natural convection is going to be able to cool this power supply in this system. So what do? Well, we have to go to conduction cooling. We're going to have to move the heat basically through a base plate or cold plate. Now, this means that the power supply has to be specially designed to do this. The components have to be mounted such that the heat is going to flow into this base plate or cold plate. And then to that base plate or cold plate, we're going to have some sort of fins, some sort of heat removal, either to air or to perhaps liquid. And so that the heat generated inside the power supply flows into the base plate and into the fins and out to the outside world. So this sounds like an interesting application. It sounds like this could solve a lot of people's problems. Matt, can you tell us about this environmentally sealed power modules?
Sure. This is what we call the ESPM. This is kind of taking the concepts you were just talking about and taking them to an extreme level. What the image you're seeing here is one of our power supplies. I like to call this aluminum extrusion the porcupine, just because of the fact that it's got these really long fins that are all anodized black. So what this is this is a hollow extrusion that we seal on both ends using these aluminum plates. And on the far end of the power supply, there are these IP-rated connections that our end customer would make. And inside this, that's where all of our electronics are. And what we actually do is we fill this enclosure with oil. So we take advantage of the heat being transferred to the oil, and then through the aluminum extrusion itself. And then the heat then gets transferred out through these long fins. So we're taking advantage of both, some convection and conduction, as well as the fact that this assembly can be bolted to, any kind of an aluminum base plate or a cold plate that could also provide some cooling as well. So, this is a very heavily engineered extrusion profile. And it's used in many different types of environments. Being the advantage of having it be environmentally sealed, it can be placed in a very, dirty, dusty, loud, hot type of environment, such as like an engine room or, an outdoor application. It can be mounted. It's been used on utility poles. So yeah, it can even be completely submerged because it's IP67. So you can completely submerge this power supply and run it at full power.
So Matt, you mentioned that black anodizing. Is that just to get a little extra cooling from radiation?
Exactly right.
Yeah.
Not to be confused with solar loading. The misconception is that, black things absorb a lot of heat. And that's true in some cases, but for a power supply like this, if it was going to be exposed to sunlight, you would use some sort of solar shield to cover the fins.
Okay. So now let's go to extreme. If we need even more power removal, okay, we're still going to use conduction cooling. But what we're going to do is we're going to basically drill a channel, run a hole through that plate, and we're going to run a coolant through there. And now, by using a coolant, like for example, chilled water, we can keep that base plate at a very low temperature. So if you remember, the heat flow is proportional to the difference in temperature. And by keeping this plate cool, very cool, like with chilled water, we can pull even more heat out while keeping the temperature in the power converter within the range that enables reliable operation and a long service life. So this allows us to do that but you know, it does come at some cost and complexity. So Matt, is Astrodyne done anything like this?
Absolutely, Bob. So one of our flagship products is called the Liquid Blade. So for scale, the conduction cooled product that we had just talked about, the ESPM, is about a 3,000 watt power supply. This particular power supply is actually 16.5 kilowatts. So it's about
and this is a 1U package.
Right, correct.
Yeah,
so this is about 5 times the power. You know, when Bob says 1U, you know, we're thinking in terms of you know, server rack sizing. So if you're you know, sizing things for a server rack, you know, IT guys are very familiar with that. You know, the 1U is about 1.75 inches tall. So this power supply is designed to fit a standard 19-inch rack. You know, it's a 480 volt in, and the output is programmable to anything from 25 volts to 500 volts. You know, just going over the design a little bit. So the coolant actually goes in through those yellow anodized ports on the left. And there are channels up and down throughout the entire design to distribute coolant to each of the channels. And the actual heat generating components themselves are coupled to these heat sink rails that actually have the coolant pumping through them. And you know, it returns. So there are some trade-offs when it comes to water cooling, just like if you were going with forced air convection, where you need to set up the infrastructure in order to support liquid cooling. You know, providing, you know, the actual coolant itself, the pump, the reservoir, some sort of radiator to actually exchange the heat. You know, a typical device that we use when we test our power supplies is a chiller, which includes all of these things.
Okay, so hey, you mentioned radiator. I mean, that to me sounds like a car. So this is kind of like a car engine. Car engine makes a lot of heat. We run water, coolant through the car engine, pump it out, run it through a radiator, dump the heat out into the air, and then the cooled water goes back to the engine. This is working the same way, right?
Yep. Yeah. I mean, radiator is just one example of several different ways to exchange the heat. Just happens to be one of the most common ones.
Okay. Okay. So we've seen now lots of different ways of moving heat, convection, conduction, liquid cooling, low power to high power. But again, if you can't measure it, you can't manage it. So just very quickly, I want to talk about a few ways that we measure temperature. First of all, thermocouples, these are the best accuracy. This is kind of the best way if you really want to get precise temperature measurements. But quite frankly, they're time consuming. You got to connect them with some sort of thermal adhesive to whatever it is. You need a data acquisition unit. But if you're going to be measuring like a whole system, lots of different points, this is probably the way you're going to go. Now, a little different thing that I actually like to use in my lab, more engineering, just when I'm doing engineering work, more than say qualification, are various kinds of surface probes. And the one up here on the top is just a fancy holder for a thermocouple. This one here actually has a thermocouple, but has the electronics to give me a direct reading and temperature that I can plug into any multimeter. So it's very simple. We can get good accuracy, but we only get one measurement at a time. So it's not, you're going to use something for a qualification testing. And there's no way to really hook these up to like a data logger very well. The other is thermography. You saw here that we can use thermal imaging. We can use cameras, infrared cameras to get a comprehensive picture. And the advantage here is it's fast. You see everything at once. If you're looking for what's the hot spot, this shows you right away. And you can get some good accuracy, but that tends to get a little expensive in the camera. And if you're looking for good resolution, if you're looking at a circuit board with a lot of little surface mount parts, trying to resolve down to some of those parts requires, kind of a high resolution camera with some special lenses. Now, the other thing that we said was very important was the airflow and understanding the airflow and like in a box. And so how do we measure that? Well, anemometers are used to measure airflow, but vane anemometers, like think of a weather vane, that's not really going to work inside your equipment, right? And you'll see a lot of anemometers are handheld. They have like looks like a little fan in reverse. That again doesn't work so much well in within electronic equipment. That's what a HVAC technician would use to measure airflow, like in a building. So what we need is a hot wire anemometer. And here's an example. And it has a little wire at the top that's heated up, and its resistance as a function of temperature is well known. As the air goes by, it cools that. The instrument measures the resistance and can calculate the airflow from that. So these are not terribly expensive, and they're pretty simple to use. All right, so I'd like you to just kind of wrap up here. There's a few key things, right? So you got to manage the heat. Just that 10 degree C rise, doubles the failure rate, halves the service life, and that's cost. That's real cost, and more in terms of warranty and customer satisfaction. So managing heat is crucial. Now, for power supplies, convection, either natural or enforced, is the most common way. But as we move up into higher power systems, we got to start using conduction cooling through base plates, and either through dumping it into air, or start looking at things like the liquid cooling. If we are using convection cooling, then managing that airflow is key. We need to understand the pressure drops in the system, understand how many CFM we're really getting, because you can't just buy the fan. You've got to really understand how the air is moving through your box. And again, as I said, if you go to very, very high power systems, and we see those, I mean, data centers are going up in power, industrial systems are going up in power, you may require some form of conduction cooling. Now, this was a pretty simplistic presentation. We didn't have a lot of time. If you'd like to learn a little more, I'd like to recommend a couple of books written by Tony Cordobon. I have no interest in these books. I've actually never met Tony. These books were recommended to me, and I found them really useful. These are not detailed thermodynamics textbooks. These just give you some good, plain talk, practical ways of understanding and managing thermal management within your power supplies and electronic equipment in general. So they're on my bookshelf, and if you're interested in learning more, I recommend them to you as a good resource. All right. Well, I'd like to thank everybody for your time and